Welcome to the viewers. We discuss an important part of mathematics, especially differential equation, special type functions. And here we consider the linear differential equation of second order. Actually, it is a complex root of function. Every nature is complex, not real. So here the treatment and idea of complex analysis is required to know, especially for the pole, regular function, etc. Now let us consider the differential equation of second order in the complex domain. And here Pz and Qz are regular for all finite z, or Pz and Qz have poles of order 1 or 2 at most at a point of complex z plane. So here we consider either regular or pole. We know already in complex analysis that what pole is and some of the idea that's required here, and now it is considered in complex z plane. Now the class of the solution of second order linear equation in the neighborhood of the ordinary point. So we have to find the solution neighborhood of the ordinary point, or regular solution point gives a new type of functions, and this type of polynomial like we call Hermite polynomial, Lagrange polynomial, and important functions like Bessel's function, hypergeometric function, Legendre functions are obtained as the solution of linear equations of particular type. We get this type of results, and this type of solution of the result that give some of the functions that creates and polynomials that will be discussed later. Now the point z0 is an ordinary point of the differential equation 1 if it is a solution of the, it is an ordinary point, and if the function pz and qz are regular in the neighborhood of z0, all other points are singular point and the singularities of d. That means other than the ordinary points, all other points are singular points. We know in the differential equation also the singular point is, and we apply this type of tools, and these singular points are the singular points of singularities in complex variable, not in real number system. Now we have to find the solution near the ordinary point. If z0 be the ordinary point of the equation, that means 1 means d2w dz2 plus pz dw dz plus qzw in this way, and if a0 a1 are two ordinary constants, then there exists a function, unique function w dot which is regular and satisfy the differential equation in the neighborhood of z0 with the initial conditions. That means they are having some of the initial condition w0 w of z0 a equals to a1 and w dash of z0 equals to a1. This is possible singularities of the function defined by the differential equation or the poles of the coefficient pz and qz. But everything that is a part of a theorem. That's why from a theorem, famous theorem, we can take it, and this is due to Fudge. So we are taking by a theorem this type of results we take, and this constant is adjusted in this way. W initial condition w of z0 equals to a0 and w dash of z0 is a1. And now let us suppose z0 is 0 if we consider, and pz and qz are regular in the neighborhood of mod z equals to r, that means real number system. Mod of complex number is real number, and then by the origin, that means of the origin, Taylor series expansion we are needed here. So pz equals to, with the criteria of Taylor series, sum of k equals to 0 to infinity pkz to the power k, and qk equals to sum of k equals to 0 to infinity qk zk. Now substituting it in equation 1, we get d2w dz2, and pz is replaced by this series and qz also replaced by this power series. Now let us substitute wz is by the polynomial a0 a1z plus a2z square etc. Then we calculate dw dz, differential calculus, also d2w dz2. Now substituting all these values, we are getting this result. So here finally substitute the value and sum of, that means for k equals to 0 to infinity, if we consider for the first term p0 z to the power 0, then plus p1 z to the power 1 in this way. So p0 z to the power 0 with this polynomial, p1 z with this polynomial dw dz, similarly dot 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 extension, and q0 z to the power 0 a1 plus this quantity, and q1 z into this quantity. Now we have equating the coefficient, that means constant term is 0. Here this is a constant term, and another term, this is also constant term, and this is also constant term. So these three are 0, that's why minus 2a1 equals to this result we are finding. And another terms that we have with coefficient of z, that is q0 a3, and here also z is this result 2a a2 p0, and with the coefficient of z, that is p1 a1 in this way. So we calculate all this result, q0 a1, this is another result, q0 a0 q1, all this substituted, we have this result, this is equal to this, and this. So minus 2 into 3a3 is equal to 2a2 p0 plus a1 p1 plus a1 q0 and a0 q1. Now we consider the general term. For general term, minus of n minus 1 n equals to this. You already see this result, n minus 1 into an minus 1 p0, an minus 2, n minus 2 into an minus 1 p1 plus dot 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 up to an pn minus 2 plus next term started from q. So n plus an minus 2 into q0, an minus 3 into q1, a1 qn minus 3 and a0 qn minus 2. And the function wz, we already see that satisfies the equation sum of k equals to 0 to infinity akz to the power k is therefore regular when mod z less than r, and this satisfies the prescribed condition at the origin. And since an is the linear combination of a0 and a1, we can express the solution in the form of wz equals to a0 z0z plus a1 w1z, a0 w0z and a1 w1z, and w0z and w1z are the solution of the differential equation, and they are linearly independent and satisfy the initial condition w0 0 equals to 1, w dash 0 0 is 0, and w1, that is w1 0 is 0 and w dash 1 is 1. And every solution of the differential equation is regular in the neighborhood of the origin, therefore the linear combination of the solution w0z and w1z we call fundamental pair of solution, that is linearly independent. w0z and w1z are the linearly independent pair of solution. And now we end our discussion today just to discuss the polynomial, just to discuss the solutions of differential equation of second order in complex plane specially, and in next times we derive from this type of equation with varying p0, pz and qz, and making different type of polynomial like Hermite polynomial, Lagrange polynomial, and find out different type of solution to get different type of functions. And let's see and watch for the upcoming videos in differential equation of special function. We end our discussion, and if you like this video, like it, share it, and don't forget to subscribe the channel. Thank you.